From the Library of Congress in Washington, D.C.
I'm Jennifer Harpster, a digital reference specialist for the Science, Technology, and Business Division at the Library of Congress. I'd like to welcome you to today's program, Our Sun, Its Influence on Climate and Life. This program is part of a series of programs. Is that okay? I'm moving along. Our speaker today, that was too far long. This program is part of a series of programs in 2009 that is presented through a partnership between my division and NASA Goddard Space Flight Center. So, what do 9 planets with their moons, tens of thousands of asteroids, and trillions of comets all have in common? Anyone? The answer is the sun, which is the star of today's program. I couldn't resist that. Our speaker today is Villanova University Professor of Astronomy and Astrophysics, Dr. Edward Guinan. Dr. Guinan has been the principal investigator for over 40 NASA-sponsored research programs that explore the behavior of the sun and stars like the sun to determine the effects of their radiation, magnetic activity, and ejected plasmas on planets and life. He has published more than 500 papers, edited 3 books, and has been the recipient of the Outstanding Research Award and Alumni Award from Villanova University. In addition, Guinan has served as president of the International Astronomical Union's Commission 42 on close binary stars and on Division 5 variable stars. Since 2006, he has served as co-chair of the Astronomy Education and Outreach Program for the International Astronomical Union. Today's lecture will begin by looking back at the young sun and how its high energy emissions played a major role in the loss of water on Venus and much of Mars's original atmosphere, and how the Earth survived the sun's early ravages. In addition, we will learn about the effects of the sun's magnetic generated energy on the Earth's climate, possibly playing a major role in the Little Ice Age, which was from 1500 to 1850. Also, Dr. Guinan will discuss the sun's possible role in global warming over the past 150 years. The lecture will conclude with a discussion of the sun's future and how the sun's ever-increasing luminosity affects the Earth's long-term climate. So please join me in welcoming Dr. Edward Guinan. I hope I didn't mess too much up over there.
Well, thank you for inviting me, and thank you for that very gracious introduction. We'll start with this one because this is the outline. It's called a tasting menu for a good reason, is that some of the topics I'm going to cover will be a taste. Some of them we may not even finish that topic because of time constraints. So I'll take you through the properties of the sun and its climate, the second part, the magnetic sun, which NASA has many satellites on board or in space. And then our program that I was funded for was the Sun in Time program. It's a look back on the sun, what it was 4 billion years ago, 3 billion years, and actually into the future even. And then a lot of interest has developed in the last 50 years on global warming. So we'll take you through that. The sun has often been blamed for global warming, mainly by the oil companies. And there's still some people who believe that it is playing a role. And then I'll take you into the future. This is the flambe of the talk, flambe dessert, because of what the sun does in the future. So let me start this rolling. And so here comes the sun. We had, if you came in earlier, you heard the Beatles song. Here comes the sun. So we found some pictures. So this is the sun. The planets are drawn to scale, but not their distances. And of course, Pluto is no longer a planet. But I left it on there for old time's sake because of Clyde Tombaugh. I knew him, and he was the one that discovered that one. So you see the distances are wrong because you can't do everything, but the size of the sun and the planets are correct. The Earth is about 1/100th the diameter of the sun, and the largest planet in our solar system, Jupiter, is about 10% of the sun's diameter. This is a little fun facts on the sun. I don't know if they're fun or not, but its mass. And who cares about grams? That's a lot of grams, 10 to the 33 zeros following. But it takes about 330 Earth masses, 330,000 Earth masses to equal the mass of the sun. The diameter of the sun is almost 1,000,000 miles across. The Earth, it would take 109 Earths to straddle the sun. The distance varies. It's about 93 million miles on average. Temperature, I put it in Fahrenheit for you. We don't work Fahrenheit, but we use Kelvin or Celsius, but about 10,000 degrees on its surface. The luminosity is how much it puts out, how much energy. And to put it into terms that you might, because that's a large number, 10 to the 26 watts, 1 second of that is enough to power us for the next 100 years. But, it's hard to harness that energy safely. But it's equal to 90 billion megaton TNT devices going off per second, which is a lot of energy. That is all taking place in the core of the sun. Down in the center of the sun, there's hydrogen fusion taking place. Its age is pinned down very precisely. It's the star that has the best determined properties because it's on top of us. It has the best mass, best radius, best temperature, and its age is precise because we use radioactive dating, isotopic dating it's called, from meteorites. And you can get it within 100 million years, which is very nice. Most stars, you can only guess their age to about 10%. Chemical composition, you wondered what it is. It's about what the universe is made of. When the Big Bang took place, it was mostly hydrogen produced and helium. The sun reflects that, 74%, 24% helium. Metals, astronomers use metals in a very loose term. Anything heavier than helium is a metal. So you wouldn't consider, neon a metal, but astronomers do. And chlorine and things like that, we consider metals. Energy source, as you know, is thermonuclear. It's the fusion of 4 protons, hydrogens, into helium, gives it off the energy, and gives off neutrinos, which I'm not mentioning. And the bottom equation is the Einstein equation. What's going on is that what happens is that energy, mass is transmuting into energy. And the way I figured it out, if you take that luminosity you see on the top, luminosity, I'm moving out of camera range, but who cares? Take that, put it into that equation, and you do the speed of light squared, and you get what it is. It's 4 million tons of matter is producing the energy. Now, you think that's a lot of matter, and it is, but the sun is hundreds of millions of times more massive than that. So the sun loses very little energy, very little mass in going through its burning. This is a quick primer, and it's very quick. Climate is very complex, but this is the simple version of it. The sun, of course, is the major source of our energy. 99.4% of our energy comes from the sun. The rest is thermal, nuclear, winds, and things like that. So the sun is the major energy source. Photosynthesis is what most of the energy goes to heating. The distance of the sun plays a role because if the energy, or the flux you receive from the sun falls off as 1 over the distance squared. So for example, if you move the sun out double, moved it twice as far away, you see that equation there, 1 over distance squared, you receive 1/4 as much energy. Thus, the outer planets are cold, the inner planets are warm because they're nearer to the sun and getting more energy. It's the same thing with sound, too. If I weren't using this microphone, the people in the back would be hearing me in that same law, 1 over the distance squared. Now, the other factors that come in are called albedo, and that's just a fancy name, or an Arabic name, for reflection. So you have that energy impinging on the Earth. The Earth is clouded. It has ice caps. So 30% of what comes in from the sun gets reflected right back into space like a mirror and has no effect on raising or changing the temperature of the Earth. Most of that is due to clouds. There's a picture of the sun, of the Earth over there. Ice caps, dust in our atmosphere, particles in our atmosphere. The blue sky you see is scattering. It's the sun's light that's been scattered, and a lot of it is scattered back into space. Some is scattered back to you. The other effects, or the emphasis, is on greenhouse effect. So you have the energy going in, and then that reaches the 70% that makes it to the Earth's atmosphere and surface. That energy gets trapped temporarily. The light that the energy emits gets through the atmosphere, but when it hits the ground, it produces heat, which is infrared energy, and that interacts with molecules such as water vapor, carbon dioxide, methane, things like that. And we have a 54, I put it in Fahrenheit again, a greenhouse effect of 54 degrees Fahrenheit. Without a greenhouse effect, we would be below the freezing point of water. We'd be 0 degrees Fahrenheit global temperature. So a greenhouse effect is good. It can be bad because then you look at Venus. Venus has what is called a runaway greenhouse effect. The surface on Venus is 800 degrees Fahrenheit. You go to your pizza place, pizza, that's about what the temperature of the pizza ovens are. So Venus is very good for making pizzas, but not much else. So what happened with Venus is it has a runaway greenhouse effect. Its atmosphere is very thick and contains copious amounts of carbon dioxide. It could have happened to the Earth. It didn't. Mars, I didn't put on there. Mars has a very weak greenhouse effect. The other factors that play a role are the energy on the Earth has to be redistributed. The equator gets most of the energy because the sun's rays come in directly. The poles, the sun comes in, and you get short days and nights and stuff like that. So you don't get as much energy at the poles. You get 5 times more solar radiation at the equator compared to the polar regions. So there's exchanges of ocean currents like the Gulf Stream. There's things El Nino, La Nina, that play roles in determining small changes in the Earth's climate, and the North Atlantic Oscillation also plays a role. But these are internal changes. That's a quick and easy picture of what's happening. You have the sun, you have the 30% being reflected, and I put on the other side the greenhouse. This is simple. It is not anywhere near as simple as this. It's very complex. This is a picture of the sun. I thought you might want to see an X-ray of the sun in sorts. This is the internal structure. The sun is a star. It's made of gas, hydrogen gas, as you saw, and helium. It is in thermodynamic equilibrium. That means the energy source inside, where you see the core of the sun, that's where the nuclear energy. It's causing the sun to almost blow apart. But the gravity of the sun keeps it from doing so. So the forces out are balanced by the forces in. It isn't going to be that way in the future. The forces in are going to overwhelm the gravity, and the sun is going to expand. Unfortunately, expand to include the Earth. That will make really solar astronomers very happy because they'll be inside the sun, but it's not going to be good for us. It happens in a few weeks. It happens in about 4 or 5 billion years. So no, don't worry about it too much. And then you see in the sun, you see the inside is about 2/3 of the way out. You reach a zone called the convective zone. And actually, I have a pointer. If I can figure it out, because I'm not supposed to leave this spot here, but I hate staying in one position. So about 2/3 of the way out, the sun begins to convect, which is a nice way of saying bubbles. So it bubbles and starts to convect here. So you get up and down motions. And when you get to the surface, that's where you see sunspots. That's called the photosphere, is the surface. Then there's magnetic effects that take place. You see filaments, coronal. The coronal region is 2 to 3 million degrees Kelvin. That would be about double that, 4 to 5 million degrees Fahrenheit. And this is all the stuff out here, this prominence, sunspots, chromosphere filaments, are all due to magnetic effects. That's produced by the fact that the sun has this convective plasma. The sun is spinning. Once in 25 days, it spins, and that creates a dynamo. like a magnetic dynamo like you would have on a generator. And that produces all of the magnetic phenomena that we're going to see. That is very important for us and for climate. This is a neat picture. They use a method called helioseismology. It's like when they use seismology for the Earth. When you have an earthquake, you can probe inside the Earth and see it has a mantle and a core. You can do the same thing with the sun. For about 20 years, a series of telescopes around the world have been looking at the sun, and the sun vibrates in thousands of modes. Remember, it's a fluid. It's not a solid, so it vibrates in seconds, tens of seconds, up to minutes. By analyzing the vibrations, you can actually determine that the sun has like an atmosphere, like our own, with circulation. The sun spins faster at the equator, that's by the red, and slower at the poles. 25 days here and 30 days up there. It's called differential rotation. And you can map inside the sun. By using helioseismology, you can look deep into the sun's core to see how it's structured. That plays a major role in the generation of magnetic fields. This is a picture of the sun, of a sunspot. But what it's showing you is I was talking about the convective zone. And these little things you're seeing here, this is sped up. It's going very fast. These little guys, first of all, this is the size of Texas. And anybody from Texas? And I had to pick a large state. And the Earth would be about the size of that center part of the spot. This is a sunspot. So these bubbles, these are rising columns of hot gas. And they have lifetimes of 5 minutes. They rise up, and then the dark part you see is them subsiding. So the temperature of the bright areas are about 200 or 300 degrees hotter than the parts that are falling down. And you can see in here that the magnetic field of the sun underneath is disturbing the flow of heat out. So the sun is transferring heat from its center by this convective boiling. And when you block it, this is about 2,000 degrees cooler in that spot than out here. So what's happened in here is the magnetic field has blocked or partially blocked the flow of heat out. And so this is a sunspot. This is a picture of a solar eclipse. Have anybody seen a total solar eclipse? Nobody? Oh, you have. Oh, good. Yeah, they're fantastic, as these people will tell you. And this is a picture of when the moon moves in front of the sun, which is this black. It blocks out the photosphere, allowing you to view this corona. This coronal region is 2 million degrees in the Kelvin scale, 4 million degrees in the Fahrenheit scale, and extends out even much longer than this, 10 times further out. Here you see prominences, storms on the sun's surface that are taking place in red. And these are great. If you have a chance to see a solar eclipse, you should do it. In China next year, there's one in August. I think it's in Shanghai. You get 2 or 3 of these a year, but you have to travel a long way usually to see one. So what astronomers do, or what solar physicists do here, is they study this during the solar eclipse. It allows you to see the corona. They discover the temperatures, the 2 million degrees. It's hot. Why is it heated? It's magnetic energy. Is that these bubbling that the sun undergoes, the magnetic effects of the sun goes, pinch the gas and cause it to be extremely hot. This is a brief history of the sun. This is a 1-minute tour of the life of the sun. The sun is born as a gas cloud, huge. It's 1,000 times the size of our solar system today. This collapses down. The center part will be the sun. The out part in here is going to be the planets. So this is where the planets will form out in there. It becomes this before it burns hydrogen, it's up at this stage. This is the sun now, 2 billion years in the future, the giant phase, and then this huge, where it becomes 150 times bigger than today. This is where we have serious problems right in here because it comes out to near the Earth's orbit or even beyond the Earth's orbit. These are actual pictures of the stages. These are star-forming regions. These are places where stars are being born. They're stellar incubators. So star, you can see a Judy Garland movie, A Star is Born, over there. And you can come back, 50 years, and you can see things change in here. Here's one that's a young star. The star hasn't been born yet. There's stars inside these columns. Here, there is a star-forming region where many stars are being born. So the sun did that 4.5 billion years ago. If you want to find the nearest star-forming region, it's in Orion. If you go, Orion is in the belt of Orion is where they are. The next stage, this is an artist conception. This is the sun, the cloud has collapsed down, is now flattened into a pancake. The central thing will end up as the star. It's called a protosun. And this has happened in the first million years of the sun's life. If things are lucky, and we were lucky, planets will form in this debris disk. 98% of the mass of the solar system is in the sun. The 2% is in the planets. Most of this gets blown away, and what remains behind are the planets. Here's the sun today. The sun will stay similar to this. It will burn hydrogen from 10 million years ago up to 9.5 billion years. So we're at 4.5. The sun is a middle-aged star. We hope it doesn't have a middle-age crisis. No, it would be bad for us. And this shows the sun now, and this shows the sun in the future. It becomes a red giant, and I have pictures of that. So my minute is almost up here. And the final stage, before that, the sun will actually convulse. When it becomes this giant star, it starts to throw out. It becomes unstable. It doesn't become a supernova or a nova. It just blows out material in a gentle way. This is a planetary nebula, because in the old days they thought these maybe were planets, but they're not. This is the core of the previous star. This was a star like the sun, went through the red giant phase, and this is called a planetary, it's called the cat's eye, as you can see, and you can see the multiple times that it had ejections. And the ejections sometimes are very complex. Sometimes you have ejections from the pole of the star. So there's tens of thousands of these planetary nebulae. They have nothing to do with planets, but this is near the edge. This is near the time of the sun's death for about 10 billion, well, not 5 billion years from now, when the sun's 10 billion years old. Now, the central object here, what will happen is this stuff will blow away, leaving behind that object there is the core of the sun. That's the ash. That's the hydrogen converting into helium. That's the helium. That's a helium core. That's what's left behind of unspent nuclear fuel. That will collapse and form the final 8. So this is the death of the sun. It forms what is called a white dwarf. And I put that movie up. Some of you may be fans of White Dwarf series. I doubt it. But if I had an audience who are 18 and 15 teenagers, they would know who this character was. But one of our brightest stars, Sirius, is the second brightest star in the sky. Of course, the sun is the brightest. A trick question that we use in our classes. This star is... So this is a star you see in the south. It's called the Dog Star. It has a companion that was discovered over 150 years ago. And its mass is half the sun. Its radius is the size of the Earth. This guy here has a radius of 2 times the size of the sun. And it's as dense as 100 million tons of water. So even I couldn't lift one of those. I mean, I would have trouble holding that 100 million year piece of a white dwarf. So the white dwarf is the skeletal remain. It has no energy left. For those who enjoy diamonds, our sun someday in the future, when it goes to the white dwarf stage, these are made of carbon and helium. It will solidify and form a diamond. This is a gazillion carat diamond. So now the next part is the magnetic sun. The magnetic sun, and these are pictures. These are not true except for that. These are false colors because these are all taken in ultraviolet or X-ray where we have no vision. These are all taken from above space because the ultraviolet and X-rays don't reach us, fortunately. The only one that's actually from the ground in real color is this guy. So here's the sun taken in X-ray. You see the storms. These are called the McDonald arches. And these are magnetic fields that emerge from the sun, and they trace out gas. This is a flare. This is an eruption on the sun having an energy of about 100 million megaton bombs. These happen quite frequently, and this is a sunspot. So this is the only one from the ground. This is actually the real colors. The dark is what actually, if you could look carefully, would be orange. So these are the NASA missions. SOHO, as it's called, the Solar and Heliospheric Observatory, has been in orbit for over 15 years, and it has a whole suite of instruments on board that study the ultraviolet. Ultraviolet is produced by hot plasma. X-rays are produced by even hotter plasmas, millions of degrees. So this is a way of studying the energetics of the sun. All this stuff here, everything you see here, is produced by magnetic effects. The spinning sun, the convection, generates these huge magnetic fields. They pinch the gas and heat it, and that's what makes it hot. So SOHO, this is a YOKO. Because of the cost of these missions, the costs are shared. This is shared by the U.S. and Japan. The previous one was U.S. and ESA, the European Space Agency. And this has made a nice collage of the sun changing with time. The sun has an 11-year magnetic cycle. It becomes very, very strong like it did in 2001. We're right in here. We're at the weakest phase, but in 4 years it'll be back here. This will create storms, aurora, geomagnetic disturbances, even could black out your or destroy your cell phone communications. Wouldn't that be a waste? Here's another one showing trace close-ups of these magnetic structures. These have about 100,000 degrees. These cool down. And these are on the sun all the time. So the sun, when you look at it, you don't know it's doing all these things. Here is this means Hinindo means sunrise in Japanese. And this is also to study the sun. And there's a stereo, which is just about a year ago. These are two satellites that are a pair. Here's the Earth, and they are separated by now tens of millions of miles from the Earth. One drifted ahead, one drifted behind, and the idea here is to take a stereoscopic image of a flare. So you can image these things in 3 dimensions and determine the structure, cross sections of them. This has some nice pictures, and I have handouts that give you resources if you want to look at this. But you would do NASA stereo, and you'd find beautiful pictures of these. It was just in the news last week, getting this picture. And a mission that's being planned for the fall is the Solar Dynamics Observatory, which has been tuned in to study what happens during the 11-year magnetic cycle. Sunspots, and now I have the how sunspots form. If this works, I have to find, this is an animation showing you what happens. These are above the sun. Now we're going to go below the sun. And what happens when you get a sunspot is the magnetic field comes up and pierces the surface, blocks the convective flow, and there you see it above, seeing the sunspots, and then you see those McDonald arch type things rising above. So this is an animation. It's not real, but based on physics. And then you have explosions. You just saw something fly off. So that's how sunspot. Oh, I didn't want to stand that a second time. Let's go on. I mean, I am. This shows you a piece of the 11-year cycle. This is the solar cycle. It's approximately 11 years between here. The sunspots are the blue. So if you track it, you see that it's approximately 11 years. We're having a low one now, and actually it's expected even to be lower in 2011. Right now, for the last 60 days, the sun has been spotless. For those who are Catholics, it's called immaculate. Immaculate is without spots. So the sun has been that way for about 6 days. Very unusual. So the sun seems to be dimming down. The sun, notice these aren't all the same. Some are higher, some are lower. What also tracks is see this thing here? Irradiance is the amount of energy that reaches the Earth. So when the sun is heavily spotted, the irradiance, which is the black curve, is highest. And that's because of all the other things. The spots block some of the energy, but they're overwhelmed by the magnetic energy, the things you saw, the flares, the X-rays, and all the other heating that take place. So that was a surprise, discovered in 1970s and 80s, and now we have tracked 3 of these. And everybody, all the solar physicists are trying to guess what's going to happen in 2011. Now, is it going to be, there's a game you play, whether it's going to be a low, high, or whatever. The game looks like the people who guessed low are going to win. Because the sun has been very, very quiet over the last year. That is actually good for us. It's good for communications because it won't, when the sun's very active, it knocks out flares, it knocks out telecommunication, it can harm astronauts, but you'll lose on aurora. You won't see as many aurora. So this is a picture of the sun in X-ray, and we're up to 2007. It would look like this. So this is taking you right around. Again, this is not optical light, but this would have a lot of spots. These are showing the storms all in X-ray, and we're right about here. And what will happen in the future is that in 2012 will be, the sun's not changing size here. It's just done to show you the perspective. So in 2011 or 12, it should be like that again. And now, just a brief, because this is a tasting, can't go into all these, this is a whole talk on its own, is solar weather. It used to be solar terrestrial relations used to be called. That isn't very sexy, so they changed it to solar weather, storms, and dangers. And I have a handout. If you want to know, every day you can get a weather forecast on what the sun's doing, which might be useful to you. Usually it isn't. But it shows you what the sunspots are doing, what the winds are, what the flares are, and why it affects us. Solar weather affects us. We're not this near the sun, thank God. We're 93 million miles away. But these eruptions, and the sun has winds that flow out, we're basically protected from most of that because the Earth has a magnetic field, which acts as a screen. It deflects the plasma around it, or it moves it into the north and to the south magnetic polar regions, which are not at the geographic pole. The north magnetic pole is in Greenland. It isn't where Santa Claus lives. It's in another area. But this is what protects us. This is probably what saved us from when the sun was young. Here's an aurora borealis, northern lights, but this is taken from the International Space Station. So the Earth's body is down here. Usually you see these looking up, and these are city lights that are being smeared. And this is when there was a plasma reached the sun, and it's interacting, it's hitting 100, 200 miles up, and causing the nitrogen and oxygen, like you have in fluorescent lights, to fluoresce. And this gives you these beautiful colors. It's a very unusual way of looking at an aurora. Now we'll see what the sun does. This is from SOHO. What they've done is they have this is called a coronagraph. They have blocked out the bright sun, which is here, allowing you to see what the sun's doing in a week. These are stars. You can see the sun is pretty active. These things that shoot out here, if they're shot in the direction of the Earth, can cause problems with communications. They can cause beautiful things too, like aurora, but they can cause dangerous things, and they have. One thing happened is a geomagnetic storm in March 1989 knocked out power in the Northeast and Canada for 9 hours. It baked these transformers. It can still do that. And so in 2012 or so, 2011, it can actually knock out our whole grid system because we're so interrelated. If something fails, then there's a whole cascade. And the sun can do this. So this shows you the Northeast. And when this happened, all these lights went out here. It also, and again, this is a whole other talk. I just wanted to give you a tasting. This is a tasting menu. Communication satellites are extremely vulnerable to solar plasma. Military satellites are protected. They have some protection, but they can be wiped out. And communication satellite means your cell phone. So a couple years ago, I think it was December 2 years ago, many of you lost cell phone communication because 2 of the communication satellites were knocked out. They're solid state. And just any little bit of plasma or geomagnetic energy from the sun can destroy them, can knock out these satellites. Astronauts in space, and they are in space all the time now in the International Space Mission, have to go to a safe room, which isn't so safe. It's better than nothing. And a major storm would actually be lethal. And so this is a problem too. This is why they've invested money into developing predictions. And when an eruption takes place, you can tell it usually takes a day to get here, a day and a half. And you can see if it is getting here or not, to whether you take protection. Military satellites are shielded, but they are also affected. And you have then what also happens is when the sun is very active, it causes the ionosphere. This is the atmosphere that's 100, 300 miles up to puff out because it's receiving solar energy, become more dense. And the satellites flying through there get drag on them, and it causes the satellite to lose orbit. Some have lost orbit. They were worried about this with Hubble during 2001, 2002, because it was the drag on the satellite. Hubble's a pretty big satellite, would bring it down. So they had a repair mission, not a repair mission, but they boosted it up into a higher orbit. And of course, the Halloween flare a couple of years ago interrupted satellite and cell phone service, which maybe isn't a bad thing. This is the project that I've been working on. Again, it's a tasting menu, so it's I didn't go to all the way changing 3 o'clock, but this is called the Sun in Time project. I had so many, I don't have that many resources. So this program uses solar proxies. So this is a program to study the sun by using stars like the sun, but younger. So we find stars that are matched to the sun but young, and then we can use these stars to see what the sun was like 1 billion, 2 billion, 3 billion, 4 billion years ago. This is the only way you're able to do this. The models for the sun are not good enough to extrapolate them back. So we gave this name the Sun in Time. Actually, there's books outside called The Sun in Time because I got my idea for the title for this project from the book. I went to a conference in 1989. So we selected these. The sun is a G2 star. We selected 25 stars. They have no rotation periods. We observed these with every satellite we could. These are X-ray. X-ray is the corona. This is the 2 million degree plasma that the sun emits. These guys are working. Chandra is the equivalent, the X-ray equivalent to Hubble. It does X-ray observations. XMM is the European Space Agency, a large X-ray satellite. These were 2 small ones. So we got time on those. The one that's working, only thing that's working right here is HST, Hubble Space Telescope, has been used to study these stars. And like we do with the sun, and like the satellites you saw, like SOHO, and the Japanese satellites are studying the sun in ultraviolet and X-rays. We're studying these stars. Of course, only a tiny fraction of these satellites are being used for this purpose. And this is the only graph I'll show. This is the log is a easy way to show this. This is a factor, a log of 10. A log of 1 is 10 times. So from 27 to 30 is 1,000 times. Okay? This is a proxy for the young sun. This is the present sun. And you see that the young sun was about 1,000 times more X-rays because it was spinning fast. And so this is the way the sun is dying down with time, because the sun is spinning fast here. One rotation in 2 days. Stars in here are 1 rotation in 9 days, 1 rotation in 25 days, and this is the future sun. And over here is actually showing the rotations. So here you have, this age is giga years, billion years, and you have this young sun, 2-day period, rotation period, sun's 25 days, and you can go on. So these are the 2 results showing the analogs. There's a lot more that you don't want to see because this is my whole project, and I'm trying to keep this short. So I made a pretty picture of it. This is the present sun, and going back in time, the young sun was spinning fast, 2 days versus 25 days, and produced giant sunspots, huge X-ray coronae, and as time goes on, these are in millions of years, billions of years, this gives the X-ray luminosity. X-ray is the amount of coronal emission, and my student made up this for me. So this is the easy picture. This is the graph showing almost the same thing. This is the hard X-rays. This is the factor of the sun has decreased by 1,000 times in X-rays, about 100 times, because 100 times in ultraviolet, and far ultraviolet about 50 times or so. So when the sun was young, it was some star you wouldn't want to be around. And there wasn't life for the first half billion years because the sun was having flares and had huge amounts of X-rays coming out of it that would be lethal to us now. And this is a summary then of the young sun. I just summarized everything in that the X-rays and ultraviolet and all that were 300 to 1,000 times stronger. The sun was dimmer because the nuclear reactions were a little bit slower then, 70% of what it is today. The far ultraviolet was a little less. The winds of the young sun we actually measured using proxies were 1,000 times today, 500 to 1,000 times. And the flares were huge. Had 2 to 5 big, nasty, killing, that would be nasty to us today, flares per day. But as time went on, the sun slowed down. The sun had what is called angular momentum braking. And this is now taking you on what it did with the planet. So this is I'm going to take you on to the next topic. Again, I'm moving pretty fast. This is a tasting menu. And there's some areas that, if I run out of time here, I have to skip. So this is a coronal mass ejection. Notice how the magnetic field is protecting the Earth. And so let's stop that movie. And we had 2 papers with using our data on the young sun for Mercury and Venus. And as you see at the top here, the sun was not nice to either one of those 2 planets. And Mercury, it was, because Mercury is very close to the sun, very, very close, 38 million miles, that it actually got its atmosphere swept away, completely gone, and perhaps it even ate into the surface of the planet, removing the outer 20 or 30% of Mercury's surface. Mercury is an unusual planet because it has a large iron core. But what may have happened is it may have been the size of the Earth and got whittled down. So Mercury is called the iron planet because it has this huge iron core. Or Earth has an iron core. Venus, further away, 70% the distance that the Earth is. But the sun, it was no match for the sun. It had no magnetic field protection. The early X-rays and ultraviolet radiation of the sun broke up the water molecule, and the winds swept it off into space, leaving Venus an inhabitable planet. The water was gone almost immediately, and then as the volcanoes took place on Venus, it just built up a huge carbon dioxide atmosphere, 100 times our own, and an enormous greenhouse effect. Earth fared better, and because it's further away than Venus. Venus and Earth are about the same size. Now remember that Earth has a magnetic protection here. So, but it doesn't protect you from the radiation. So the X-rays, the far ultraviolet and ultraviolet radiations get to the atmosphere, and they cause photochemical reactions. They break up carbon dioxide, they can break up water and do things like that. And they can cause the ionosphere to puff out. One of the things that, and the winds are very strong, but for the most part, the magnetic field of the Earth, which was stronger than today, protected its atmosphere from being blown away. These reactions are good and they're bad. They sterilized. If any life was there 4 billion years ago, it was sterilized. But 3.5 billion years ago is the first evidence of life, continuous life for the Earth. One of the things it can do is down here, is that these photochemical reactions that are quite complex, that break up molecules and allow new molecules to form. One example of it is this nasty thing, formaldehyde, which is a carcinogenic material. Maybe if you're older, you remember frogs were put in there, and we played with them, and we didn't know it was not a good thing to play with. And formaldehyde is actually a useful thing in the building block of life. Formaldehyde is made can be made in our Earth's early atmosphere by breaking up carbon dioxide into carbon monoxide, breaking up water into hydroxyl and oxygen. And then these two come together, forming HCO. 2 of those go together, forming formaldehyde. So it could have played a role in development of life. And the reason for that is that the key ingredient of formaldehyde, when you put 8 of them together, forms ribose, which is one of the key ingredients. It's a sugar, and one of the key ingredients of RNA. So it could have aided in the production of life on Earth by giving the energies for these chemical reactions to take place, and of course, life. I gave this talk at Halloween. I never took it out because I like Frankenstein. So what I don't have a lot of time for is Mars. Mars did all right. Mars is further away. It's 1.5 times further than the Sun, so it receives half as much radiation. But Mars is a little planet. It's 1/10 the mass of our own, so its gravity is weaker. It has a harder time retaining an atmosphere. Mars has water. It's 100%. It used to be an argument 20 years ago whether Mars had water or didn't have water. It has water. It's frozen. But the arguments where you see evidences of dried up riverbeds, these things, these kind of sedimentary rock. So I used to have a whole song and dance 10 years ago where I would do 5 minutes trying to convince people it has water, but it's of course frozen water, although once in a while it bubbles out. So I no longer have to worry about that. And this is the most convincing thing. This has not been released yet. So if you didn't believe it, now this is, and again, I'm giving myself just 2 minutes to do this. This is one of my pet projects. We received some money from NASA to use our solar data, and then we modeled it. We took an early model of Mars, and we saw what happened. This is Mars presently. Mars is not a nice place. Its atmosphere is 1/90th as thick as here. That means you have to be 20 miles up. 20 miles up, it's hard to breathe. You know, there's not much air up there. It's cold and dry. It's minus 50 degrees Fahrenheit. It has some ice caps. Carbon dioxide, for example, exists there because it's so cold. It's made up of mostly carbon dioxide, but it's very thin. It has iron in its soil, iron oxide soil. But the bottom line here is tectonically dead. That means it doesn't have active volcanoes or plate tectonics. And it has a solid iron core. The liquid iron core is what produces magnetic fields. So it has no magnetic field to speak of. Old Mars in the past, 3 billion years ago, giga-year, 3 billion years ago, appears to have an atmosphere about our own. Our atmosphere is 1 bar, so it's what we have. It was warm and moist because that's what gave you the rivers and the lakes and things like that, and the sediments. So it had liquid water oceans. We've computed the oceans could be 50 to 100 feet deep. It had these gases, even oxygen. It had a strong greenhouse effect because it had water vapor. And it had a liquid iron core. It had a magnetic field because it has ghost relics of magnetic fields. And it had, therefore, a magnetosphere. That's that protection that the Earth has. Unfortunately, Mars was a smaller planet. It cooled off. The magnetic core solidified after about 1 billion years, leaving Mars open to the ravages of the sun. So the sun's gases, the plasma, swept away. It broke up the water molecule and took away much of its water. This is how Mars may have looked in the past with the oceans. Leaving behind, the oxygen got blown away or dragged off into space by the solar plasma. The oxygen, heavier, got incorporated in the Martian soil. And fortunately, it didn't all go. As Mars lost its water is a very strong greenhouse effect. Mars's temperature cooled down, water froze out, and this process slowed down immensely, leaving Mars with water. Ice water, but still water. So this is Mars 3.5 billion years ago when it had a magnetic field. It was protected. But what happened when that went away is that the magnetic field went away. The ultraviolet radiation doesn't care about magnetic fields. That got in and broke the water molecule up, and the winds of the sun dragged off the hydrogens into space, leaving it the way it is today. The last 1,000 years, so we're taking you up to the present. This is an old painting by Bruegel in 1565. This is about the Little Ice Age and beyond. And did the sun do it or not do it? There's a lot of, we go back to this picture again, and here I put in that these gases here, since the last 150 years, have actually increased. So this is the same, the sun is the same, but in here, these gases, the greenhouse gases, have gone up 30% for this guy and 100% for that one. So sunspots. The first sunspots were seen by, or plotted by Galileo in 1609. He had a telescope. There's a nice exhibit in Philadelphia, if you want to see it. It has his telescope is there. And sunspots are a measurement of activity. So if you plot 400 years of sunspots, you see that Galileo was doing work here. And then there was this period where there were no sunspots for a long time. And then you see the sunspot cycle. This is what we have today, this 11-year cycle, lots of spots. So every 11 years you get, notice they're not the same. That's why it's called a cycle. Sometimes you get higher ones. Sometimes you get little ones. Sometimes you get none. This has a name. It's called the Maunder minimum. And coincidentally, or maybe because this happened, it ends up that the little ice age occurs at that time. We also had a period of no aurora. You have records of aurora. There weren't any in the 1700s. And then I plagiarized this, the little ice age, this is called, from about 1450 to 1850. The Earth did cool down. There's lots of evidence from direct evidence. There's this, the ice pack began to 1250, the Atlantic ice pack began to grow southward. Glaciers began to grow, and so this is getting colder. So the 1300s, you had rains, famines, you have glacial expansions. All this is indirect evidence of even these things. The Swiss Alps glaciers advanced. People used to go skating on the Thames. You would never do that today. You fall through. Alps getting bigger. Some people even claim the Norsemen found Iceland and Greenland. Well, what happened in here is that these colonies in Greenland had to be abandoned because it got colder. Pictures, you can go, there's a study made of art in this time. Art scenes are like this. You see people skating on rivers and art scenes that show snow and ice. Now, beer. Why you drink beer? In the 1500s, the major drink in Europe, you couldn't drink water because it was all contaminated. People used to throw their garbage out. Grape is very sensitive to climate, but barley isn't. So because the wine prices got so high, they switched over to beer, and that still stays the same. Bottom line, this is the picture. These various little colors and everything are different methods that are used to get the climate. So here you see the present. The present is 1,000 years ago, and this is taking you up. It's 2,000 years ago. You see it was warm, it got colder, so this is the ice age. The black graph in here is instrumental. This is actually using thermometers. Notice the steep rise here from 1850 or so. This is a movie that shows from 1500. Again, I have to skip around because I want to get this done. So blue is cold. So this is 1660. This is a little ice age. And now it will start to warm up. As you see, orange. And then you have the present. A lot of the present has nothing to do with the sun, though. Then you get out of that scheme. So bottom line, the little ice age happened. It was probably the sun played some result, but volcanoes were also taking place at the same time, and the North Atlantic Ocean had a cool current coming down. I'll jump to and this is global warming in the last 150 years. So I'm covering a lot of turf here. So this is a recent issue of Sky and Telescope, where should we blame the sun? 20 years ago, half the people did blame the sun, including me, but I had to change my mind because the sun is actually not getting brighter. It's actually cooling down. So that will be the answer here. And these are evidences of global warming are everywhere. Here's glaciers, 1920. This is where it is now. So the glaciers are all retreating. This is the Arctic Ocean. This is 2000. This is 1979. It used to be that extent. Now it's 2007. Soon you're going to have an ice-free Arctic Ocean, which will be great for commerce, but not great for climate. And then you have these pictures of polar bears, in danger. I just saw that lady last week who jumped in. They're not nice. She jumped in Germany to hug a polar bear. It didn't hug her back. So as you know, the Industrial Revolution was the 1850s. It got really in full swing by 1900. So you have carbon dioxide, cattle producing methane, and you see then this is the increase in carbon dioxide. The little whips, little things you see here are seasons. This is taken from Hawaii. This is the temperature rise in 1860. It actually tracked the sun for a little while right in here, but then the sun kind of leveled off. You'll see that picture in a second. Notice what happened. Look at these rises. This is carbon. How do you get this data from ice cores? You go into the Arctic and you bring up ice and the little bubbles. You can analyze how much carbon dioxide or how much methane or how much nitrogen there is. And these are this is a 30% change since 1880. And you plot it on this. Here's a blow up of that last. And methane, which comes from cattle or rice farming, really rose up like double. And these are all greenhouse gases. This is from the Intergovernmental Panel report. And I'm going to skip that one and give you the bottom line here. This is taking all the data that there was from 1900 onward, where you get the different contributions of each element to climate, to temperature change. So here you see temperature change in degrees centigrade difference. Fahrenheit, just multiplied by 2, and you'll get the Fahrenheit difference. This is the amount of watts, the forcing. Forcing is when you make something happen. It's like when you force. When you make the sun warmer, it will force the climate to be warmer. So what they've done here is that since 1900, the sun has gotten a little brighter, which was true. But notice what happened here. The sun has leveled off. And that kind of tracked what you see here is the observed. And yeah, there was a little correlation between the sun and the climate. But look and the sulfates here are from volcanoes. That makes it cooler. Anything below this line makes it cooler. So our pollutions that produce carbon dioxide also produce dust and things like that. So that actually compensated, the soot and things like that, compensated to some extent, mitigating the temperature rise. You have volcanoes in green. That's Pinatubo over here, right there. And ozone changing. So the bottom line here, when you put in all the effects, and this is due to carbon dioxide and methane, is this blue one. When you add all those curves together, this is the model, that gray or mustard-looking curve fits, and fits extremely well. And notice the sun, if you just put the sun there, it has a little influence. 2/10, 1/10 of a degree. The sun did cause the Earth's temperature to go up 1/10 of a degree. If you're from sun oil, you would be very happy about that, but that isn't enough, because this is a rise of almost 2 degrees. So the models fit, and they're getting better and better. These are supercomputer models. And here's the smoking gun. I plot here. Now again, if you were doing this work long ago, you would have then the solar variability. This is the Maunder minimum, where the sun was dim, and the scale is what the temperatures could be. The black is instrumental. That's using thermometers. So back here you have to use pollen or glaciers and stuff like that, so there's uncertainty. But notice what happened here. The sun is actually not as active. It's leveling off and getting dimmer slightly, but notice the temperature rise. And if I went up to 2008, that would be here. The sun would be there. So this is the smoking gun, and it's reliable sources using everybody's data, and that's from the report. This is if you wanted to see the future, and if you want to see the future, these are the projections. If you keep things going the way they are, carbon dioxide, or depends on China, India, you have to play games here whether we put caps on carbon dioxide. you get this picture here. This is the 2020 to 29. Again, the coding is down here in degrees. Black is 7.5 degrees centigrade. That's 14 degrees Fahrenheit. So here you see the best model, not the best case scenario. The middle one is the most likely. But here you see in 2090 to 2100, notice the purple. It's 7-8 degrees, 10-degree rise in temperature at the poles, which melts the ice caps. We don't fare so well either. The Earth is much warmer everywhere, except in a few places it's not as bad. So this is the worst case scenario in terms of what can happen, and this is the most likely. And this, if you want to see what happened to the U.S., this is the U.S. These are temperatures in July. So here's 1993. These were modeled, and they worked. So green is, they give you scales here. Yellow is 90 to, this is a high temperature in these places in July. So this is what you get like now, nowadays, I would say. Here is Washington, right here, in 2085. Some of us may be here, not many, but some of us. You notice that the red that you think it's hot now, is that you would have many, many days between 100 and 107. And these poor people down in here are having temperatures like you get in Phoenix, 107, if the models are correct. And I'm going to do sea levels. Sea levels, black is like 1 foot. A meter is 3 feet. So this gets extreme. But the bad part is New Orleans. Mississippi is has very little chance if the ocean level goes up, because the glaciers run off and the heat of the oceans make the oceans expand. So the ocean level rises because of two reasons. Hot water expands, and also the runoff of the glaciers. So where you see red won't happen for 100 years, because that's you're talking like 10 feet. But you notice that the coastal southern California, southern Florida is affected, and where you see black, that's affected immediately almost. And I had a blow up. You see Washington. I hope you don't have land properties too close to the ocean, because that's the Chesapeake floods. There's already those two little islands, and the Chesapeake are already going underwater. They go underwater in about 20 years. I forget those two islands. 10. Don't buy land there. They have very good crabs. And this is Florida. Well, you're okay. Those who are fans of Disney World, you're okay. But this is what Florida was. This is extreme. 16 feet is not going to happen in maybe 300 years from now if everything continues. But this is Miami. So maybe a few places might be above sea level there. So it's pretty dire for a state like, where the highest point in Florida is 150 feet above sea level. And now, you're all looking forward. This is the end. This is the this is the flambe. So this is, in 1 minute, you're going to see the future of the sun. So here's the Earth now. We're in the habitable zone, 93 million miles. That doesn't change. We have a friendly sun, sort of. But the sun is getting more luminous as time goes on, because the nuclear reactions are getting faster. The sun's interior is getting hotter, and the sun is expanding. So 2 billion years from now, it's already the end. Because what happens in 2 billion years, the sun is 25% more luminous. That makes the Earth 15 degrees warmer. But that's not what happens. It triggers a runaway greenhouse effect. The warmer Earth produces more water vapor. Water vapor is a strong greenhouse gas. The carbon dioxide comes out of the oceans and makes the Earth run away. It gets hotter and hotter until the oceans begin to evaporate even. So life on Earth as we know it is about 1 billion years. Now again, 1 billion years is a long time. It's not tomorrow. But it isn't 5 billion years. This is what happens in about 1 billion years. Things become uncomfortable here. Forgetting what we're doing. It may happen sooner. This is natural. This is the sun. This is the normal course of the sun's life. The sun is becoming a red giant. here it is, 4 billion years from now. This is how the sun will be. You'll look up in the sky and you'll see a beautiful red giant. It'll be beautiful. Near, and it will fill up half of the sky in red. But on that time, there's no one living, no, not even cockroaches will be living on the Earth. The temperature of the Earth will be above the boiling point of water. It will have no oceans. It will be barren. Maybe a cockroach can be here, but that's about it. And then it will go a little bit ahead. This is a depressing end. This is showing you at that stage about 5 billion years from now. This is the sun looking down from above. Here's Mercury, here's Venus, here's Earth. Notice the sun is here. And so we're in it. And that's great for a solar physicist. You get to actually see inside the sun. And this is the sun 5 billion years from now. The Earth incinerates. So here's a picture that my student made up of the Earth incinerating. And then I have a picture in Vietnam. I think this was taken. And this, you'll be very happy. This is the last slide. Showing. And thank you. Okay.
This has been a presentation of the Library of Congress. Visit us at loc.gov.